tell. So before we start today, I wanted to review a couple of quick things. One thing is I was lying down and maybe just about to go to sleep and thinking about this class just like you do all day long. And I thought, if you never wrote a program before, loud? It sounds like the volume is loud. Maybe can we turn it down? Can you make it lower? Is this low? Maybe right there. How's that? Okay. All right. So if you haven't done a program before, maybe the basic idea of a program, I should have been more explicit right at the beginning. So what is the basic idea of a program? We put in a lot of commands that we would normally have to do one after another, after another, after another. You put it into one group. And when you run the program, the idea is the program itself becomes like a new command that you've invented. Like you invented a new key on your computer. And if you push that program to run, it does all of the commands that you put inside the program at once. Right? So that's the basic idea. Is that really obvious to everybody now? Okay, good. And inside the program, the first couple of examples we've done so far, inside the program we have something like 10 commands, so it's not that big a deal. But some programs can have thousands, tens of thousands, millions of commands. And it's a big deal. So now that you've thought a little bit about things like base 2, base 16, ones and zeros, right? Think about when you click a button, say Internet Explorer, and it opens up that Internet Explorer, it's connected to the internet, maybe it shows you Yahoo, or maybe it shows you, whatever other homepage you like, MTV, whatever it is. Think about how many commands have been programmed by somebody like you between you pushing that one button and that thing that appears on your screen. It's remarkable. Okay? So that's the idea of the program, is to take a set of commands. Each line is usually called a command, right? You tell the computer something to do something, it does one thing. Now, underneath each command can be another sub-program, like we talked about yesterday, the idea of a subroutine or a function. So maybe one of my commands is, right? So to me, that's one command. But to the computer, in order to evaluate this thing, it has yet another subroutine, a sub-program. And that sub-program maybe has another 30 commands or 50 commands in it. And possibly some of those are even more subroutines. So there's a hierarchy made up of pieces, and each piece is a set of commands that you don't have to repeat over and over again. So that's the beauty of it. Okay, so does anybody have any question about the motivation for why you should learn how to write a program? I hope it's clear to you what the potential benefit is. And as I said the other day, in a way it's a little bit of a shame maybe that the timing between this class and 208 wasn't exactly the same. Because I think in 208 you got some homework that this class would probably have made your life a little bit easier. You could have written some programs early in 208 and used them over and over again to do certain kinds of calculations in there. But that's okay, you can do it in the future. Okay. The second thing I wanted to say, lots of comments. Now, in this instance, comment refers to a special kind of command that you put into the computer. What kind of command is that? Do you know? It's a weird command. It's basically a command that says, ignore what's following this. Just skip it. Just go to the next thing. Right? A comment is your note to yourself or somebody else who looks at your program. It's not for the computer, right? So it's something that's sort of like you whisper on the side. Now, I believe, especially if you're a beginning programmer, you should use a lot of comments. What's interesting is the best programmers in the world use the most comments because they know how important it is. It's important because you want to write a program that you can then reuse over and over again, maybe for the rest of your career, if you write it correctly. For instance, the sign, once you write this program, you don't want to have to go back and ever change the sign. You just leave it alone and use it when you need it. But just in case you ever need to go back and look at it, it really helps if you explain to yourself what it is that you're doing inside the program. Explain the commands that you have in there. Okay, so in the middle of your programs, I recommend having a comment, many comments through the program to remind yourself what it is that you're doing. Some programmers put a comment line in between every actual command. So every single line in the program, they remind themselves what it is they're doing. I don't know if it's important to put in that many, but there's nothing wrong with it. In the bad old days, when I was a student, there weren't terminals. You couldn't type commands into a computer like you do today. The only way to put a command into the computer was through some physical device. And the most common one was a card. It had a little cutoff at the corner. Have you ever seen these? The length is something like about 20 centimeters. This is probably about 8 centimeters. You never saw this? Okay. And the card was made from very heavy paper. Almost like a cardboard, like the cover of the cover, sorry, like this part. Not paper, but like that part. And the card had 80 columns. One, two, 80 of them across. Each column had the possibility of about, I don't know how many, probably 40 or 50 characters. Okay? So 40 or 50 rows. I don't remember the exact number. But it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, A, B, C, D, so on. Right? Now, there was a special machine that looked like a typewriter, which is another thing that belongs in a museum. Do you know what a typewriter is? The old-fashioned typewriter? Okay, this looked like a typewriter, but it actually punched holes in the card. Okay? So if I want to put in a command like C out, A equals A, line in. Let's say I want to put in a command like that. First of all, the command has to be less than 80. And in fact, that's not even quite right, because out of 80, the first 6 you couldn't use, and the last 7 you couldn't use. So in between that, usable, there were 67 columns. So I have to count 1, 2, 3, 4, 5, 6. It has to be 67 or less. Okay, then I sit at the computer and I type this line just like that. Not the computer, sorry, I sit at this machine called the card punch. And what it does is it punches a hole for the little C, then in the next column it punches a hole for O, and the next column it punches a hole for U. So when I'm done, I hold the card up, and the card has a bunch of holes punched in it. Okay, that's how you put a command into the computer. Inside the computer was an optical reader, so there was a light on one side. When the card got in front of it, the light would come through those holes, and there was a receiver on the other side that could tell which holes were punched. That's how you put the information into the computer. There was no such thing as a keyboard like this. It doesn't exist. You can't do that. So if I want to write a program, like the ones that we're doing in here, I end up with a stack of cards. Real cards. I have to carry them around. Real hardware. It doesn't exist in the computer. I own it. I carry it. If I want to run it, I have to go to one building on campus where the computer is. And there's a window like a bank, right? Thick glass, a little slot at the bottom because the computer was too valuable to let some jerk like me or any other student come behind the glass. So there's a guy behind the glass that runs the computer, and I would hand the cards in under the window, and he takes the cards and he puts them in the computer, and he goes, it reads them one at a time, and then the computer runs, and then after a little while, the output comes out, and then he gives me the cards back and the output back. That's how it worked when I was your age, when I was a student. Okay, now, why did I tell you that story? I told you that story because writing a comment in those days, it actually was a lot of extra work. Because for one thing, it meant having a bunch of extra cards that I have to carry around. And I have to type them in, and I have to punch these holes. So in those days, you had some reason why maybe you didn't want to put so many comments in the program. Today, there's no reason. Right? Your computer won't be any heavier. If you put 1,000 comments in your program, your computer is still going to weigh the same thing. You don't have to carry 1,000 extra cards. Okay, so use lots of comments. Okay, another suggestion. It's related to number 2. When you're writing your names, when you make up names for your variables, I think it's very helpful to make a useful name. Don't just be silly with the name. Put some name in there that you'll really remember later. Right? Like we did a program yesterday to calculate the average of 3 numbers, and the name of the average was AVE. That's not a bad name for average. But you could even be better, right? You could just call it average. It means a few extra key strokes to type that in the first time, but then for the rest of your life, when you go to look at that program, you'll always remember what that variable is. So that's the idea with these 2 suggestions. Okay, then actually I have one more. And that's debug with lots of cout. Okay? So what do I mean by that? When you're first writing a program and you're not sure yet that it's going to work, I think it's very helpful to put a C output command almost everywhere, maybe after every single line. And you can check one at a time every calculation and make sure it does what you think it's doing. And then after you figure out that the program, okay, it's working, then you can go back in front of those lines, and for a comment, I think the comment is this, right? Does anybody remember? We'll open up one of the lectures because it shows inside there. But I think the comment symbol is this. So you can go back. What does this mean? You think it's something else? This way? Okay. See, from where I'm standing, it depends on, because from where I'm standing, you can go in there to all of the C output statements afterwards and just add that at the beginning. And then they won't execute the next time they become a comment. So it's not really any problem. You can leave them in there. I mentioned before, anybody know what that is? Somebody do the microwave on? Yeah. I mentioned before that in the debugging of a program, there are 2 main kinds of errors. One of which is obvious, and the other one of which is a killer. It really sneaks up on you, and you can really be very frustrated. Right? So the obvious one is when you make a mistake in the syntax of a command, and so the command just doesn't work. Like maybe you forget to put one of those in. Then when you go to run the program, it stops. And the program itself tells you there's something wrong with this statement. But the ones that aren't so obvious are a command that works. That command works. But does it give you the average? No, it doesn't give you the average. It gives you A plus B plus C divided by 3. The average should look like this. A plus B plus C divided by 3. So it's that second command, it's this kind of mistake that drives you absolutely crazy when you're writing a program. Because the command works, the computer doesn't say there's anything wrong with this. Right? That's fine. The computer's happy to make that calculation for you. But it's not the calculation you want. So I think it's a good idea to put C output, just after every single statement. And then maybe the first time that you run your program, you have a calculator on the side. And line by line, you go through, you calculate what you think each line is supposed to do, and compare it with what the C output says it actually got, and make sure that you've put them in correctly. So that would be my first suggestion. Okay, any questions about that?
Actually, I have a question on the exercise 2.3 that with the what is the optimum cylinder?
Yes.
When I calculate the R from B, this doesn't have to work. But how do I relate it to the R at the second time? I mean the second stage, the A equal to 2R, R equal to 2H.
Okay, maybe we'll kind of, let me catch up with you. We'll start over a little bit. So, by the way, Andy and I discussed the words optimum cylinder yesterday, and we agreed that neither one of us ever heard of that before. So, if you never heard of an optimum cylinder, don't worry about it. Sometimes people, this comes back to the idea of the specialties and the different fields. So within a certain field, they develop their own special terminology. So optimum cylinder, that must be some special terminology from fluids or something like that. But neither one of us ever even heard of an optimum cylinder before. But optimum cylinder, then, if I remember right, it's supposed to be the D is equal to L. Is that? So it looks something like this.
That is
Okay, and the volume, what would the volume then be?
the base.
Should be the area times the length, right? And what's the area in terms of D? Pi D squared over 4, right? Times L. Okay, so let's turn that into a C++ command. Now, the exercise assignment asks you to find what, L or D?
This need to be L and D.
L and D. Okay, so in the optimum cylinder, they're the same thing. So this should be equal to pi, let me put the 4 out here, pi over 4 times, I'll call it D. Okay, so now to solve for D, we need the cube root, right, of 4 times V divided by pi.
We will have the function of the root of 3 in the C++ kind of time.
Okay. So you were looking for something like a function maybe with a name like cube root, something like that. Did you find square root?
Yes.
Yeah. So here's one thing you could do. I'm not suggesting that you necessarily should do it. You could create your own new program for the cube root. How about that as another exercise? Does anybody know the algorithm? What's the algorithm for finding a cube root? So let's say we want cube root of x. And then I'll call it y. So what would the algorithm be for calculating y? If you're given x, if you know what x is and you want to calculate y, how do you do it? What's the algorithm? Okay, you want to come up and write it? Write the algorithm. before you do that, I want to pause. You come up, it's okay. But so, how many of you think you know the algorithm of this? How many of you think you ever knew the algorithm of this? Maybe in a high school algebra class or something like this, the teacher showed you this one time, but in the last 3 years or 5 years, you never did it, and you completely forgot in the meantime. Okay, so this is based on the idea that you take x cubed is equal to y. So you took the log. So 3 times the natural log of x is equal to the natural log of y. Right? And now this is y, right? So raise both sides to the e. I think in your exponent you probably should have 3, right? I think you have the 3 in the denominator. It should be here.
No, what? No, it's not the part. We take the square of cube be divided.
Yeah, the cube root of x is, oh, you're right, this should be the other way, right? Cube root, the way I wrote it, y is the cube root of x, yes, sorry. So natural log of x is equal to 3 natural log of y, right? So natural log of y is equal to natural log of x over 3, right? And so that's how you get this. Okay, so that could work, right? In order for that to work, you would need to find the function inside of C++ that does natural logarithm. Did anybody look for that one? You did look for it or not? You did? Okay. So, and you found the natural logarithm, I'm sorry, the function to do e to the power something. Does this calculation?
Yeah, I calculation, but I convert e to the 10, and take the exponential of the 10 and the logarithm based on 10, not based on e.
Okay, that's okay. Yeah. Okay, so does everybody understand what he did? It's clever, right? So he couldn't find the cube root function. So he wrote his own algorithm to calculate the cube root based on this. And then you can write a function that uses, it means these other two functions, which you have to find or else write more subroutines. But he found one for the exponent, but he used 10 instead of e. That's okay. And one for logarithm. Okay? Alright, now I think that's not necessary though. I wanted to go through this exercise because I want to remind you that this is always in your power. And when I was a student, the number of subroutines that had already been created was much, much smaller than it is today. So these days you can find a lot more things that have already been put into the program than there used to be. So when I was a student, it was really common that you might have to do something like this to create your own function. And I think it's helpful for you to know how to do this, to realize you always have this power. Right? Congratulations. That's very impressive. I'm serious. However, I believe that you can calculate the cube root easily in C++ because I think you can raise something to a fractional power. So cube root is the same as something raised to the power of 1 over 3. So you can write d to be equal to 4 times b over pi raised to the power of 1/3. That's what this means. And I'm pretty sure, not positive, I'm pretty sure C++ will let you do this. I mentioned yesterday, I don't want to keep reducing the importance of C++, but MATLAB, which comes at the end of the semester, I think many more engineers use MATLAB, and MATLAB has all these functions built in. That's never a problem with MATLAB. MATLAB will definitely do this. Okay, so maybe I need to learn with you whether C++ will do this, but I think it will.
Taking the programming when I change from double to the float, it doesn't change much about the result. Because in float I will find the 6 digits, but also in the double I only find 6 digits instead of 12.
Well, maybe the output statement needs to be adjusted to show more than 6.
I think the number I put is a really, really beautiful and mistake a lot of number. I count it in my hand, and after I put it in the program, it only appears 6 digits. It's still a 12 that I expect.
And did you have in the double command, you declared all of the intermediate variables that you used?
Yeah, I set up in the normal formula, and after I put some value, I change from double to float. The result doesn't change the number.
Yeah. So that's I guess that's an example. There's no rule, right? So it depends on how many calculations you make, and it also usually depends on how big the difference is between the numbers. So like I gave the example the other day, I'll do it again. If I add 10 million plus 1 minus 10 million, in float, the answer to this is 0. In double, the answer is 1. So what's the key that makes the difference? The difference is how much difference in size there is between these numbers. So if you do a calculation where most of the numbers are about the same size, then when you add them or subtract them, the first 5 or 6 digits should still be accurate. The problem with the last 5 or 6 digits, it usually comes up in one of two situations. One situation is that the numbers that you're adding or subtracting are much different in size, like these are, and so you lose the accuracy because of the size difference. The other one would be if it takes a lot of calculations, thousands and thousands and thousands of calculations, and every calculation has to be stored, and then it calls it back out and uses it in a new calculation, stores it, calls it back out sometime, uses it in a new calculation and stores it. Every time you do that, you lose a little bit of accuracy at the end. So if there's a lot of calculations, you can also lose accuracy. But if there aren't too many calculations and the numbers are more or less the same size, float should be still pretty accurate. So I think that's why you don't see a difference between double and float for this example. Okay, other questions about that? So that's exercise 2.3. Everybody's okay on 2.2? Should we review 2.2? Who would like to review exercise 2.2? Yes. Yes, but do you have A equals B after B equals 3 or before B equals 3? Yeah, but then it should be 3, eh? Okay, so it doesn't know what B is.
So it has to be step after step.
Yes. Yeah, the C++ cannot do algebra. Okay? Now that sounds like a very simple statement, but it's very easy to confuse yourself on that one. So let's talk about it. Right? It can't do algebra, it can only do arithmetic. A equals B, that's algebra. So A equals 3, that's arithmetic. Now, this is where it gets a little bit tricky. It's okay to do this after that, because now it knows B is also equal to 3. But if I do this first, like I think this is what you said you did. If you do this one first, then you do this one. Or maybe you do this one after this. It doesn't know what the value is. You didn't tell the number yet. So I think think every computer maybe is a little bit different. I'm not an expert on this. I can't say exactly what happens now. But I can tell you back in the old days, and this is probably still what happens. Remember, when we say at the top of a program, we start off by saying double, A, B, C, make a list of numbers, or variable names, average. So what happens in the hardware when we do this statement? It takes some piece of hardware and it sets aside space to store 12 numbers, and then a couple of more numbers that go with the X bar. It's like the power of 10, and this is the X bar. So physically, inside your computer, in memory, it sets aside those spaces. Okay, now, maybe last week you had a video in there, or an MP3 song, or an email. Who knows what was in there? So the space that it sets aside where it's going to store A, there's something already in there, because probably your memory isn't brand new. It's probably been used for something else already. If you say something like A equals B, and you haven't changed it, then this thing could be completely random. Who knows what it is? It could be part of a song, it could be part of a video, who knows? But as soon as you write this, then that piece of hard memory becomes free. And now if you say B equals A, it knows when it goes to get A, it gets free instead of something that's random. Okay? I'm sorry that you had trouble, but I'm glad that you've come up with your own version of an example of exactly the kind of debug statement that I keep saying is so hard to figure out sometimes. Because C++ has no problem with this command. That's a legitimate C++ command. It'll run that command. But when it runs it, it may not do exactly what you intended for it to do. And those are the kinds of errors that are the hardest to figure out. Why doesn't this work? It looks right. The computer does something, except it doesn't say there's an error. And yet, the thing it comes back with is not what I want. And those are the kind that drive me crazy. So I'm glad that you have an example of that. I hope you don't have very many more examples of that. I hope maybe it's your last example of that. Oh, darn. Okay. What's the other one?
Say A equals B, A equals B equal A, and C equal A plus B plus C. And it's still done with the compiler.
Yeah.
The answer is wrong.
So you said A equals 3, you said B equals A, or B equals 3?
B equals A.
Okay, that's okay.
That's okay. And C equals A plus B plus C.
Yeah, so what does the value of C when this statement begins?
Just C.
Yeah, but it doesn't know, right? So that's algebra, not arithmetic, because you didn't tell it what C is yet. Okay. Actually, this is a good point, because look at the difference. This I hope is really helpful to understand. It's tricky. The logic can be very misleading, right? If I write this statement as an algebra statement, right? What's the answer for C? There's only one number that works for C, right? There's two possibilities here. Either A plus B must be equal to 0, or C must be equal to 0. In algebra, that's the only way that statement can be true. Is one of these two things has to happen. Well, yeah, so the only way it can be true, you're right, so this isn't even possible. That's the only way that can be true. That's the only way that can be true.
So that means A equals B equals C equals 0.
Okay, now let's go back over to C++. What's the difference here? So suppose I do this. You had this statement next, but let's suppose that your next statement was this. And then you had this statement. What's the answer for C? You said that. Somebody else said that. So in C++, if I put these three statements in, what's the number? Remember, somewhere in the middle of the computer, I guess I just erased it. Somewhere in the middle of the computer, there's some ones and zeros that represent the value C. At the end of this statement, what is stored in there? 9, right? Because there's also a place in here. There's one for A, there's one for B, there's one for C, there's one for average. 4 different pieces of hardware inside the computer because of this statement. There's 4 pieces of hardware that store values. Then this statement comes along. What happens? The place in the computer for A becomes 3. This statement comes along. B equals A. What happens? The computer comes to the A, it takes those numbers out, makes a copy, pops them into B. So now B is equal to 3. This statement comes along. It takes out C, which is equal to, it takes out B, which is 3, and puts it into C as a copy. Now A, B, and C are all 3. This statement comes along. What happens? It takes out 3, 3, and 3, adds them together. It gets 9, and it puts it back where the C was. So now C is equal to 9. So this statement is an okay C++ statement, as long as it already knows what A, B, and C is. But if you didn't yet tell it what A, B, and C are, this statement won't do anything useful. For exactly the same reason. If it doesn't already have good numbers for A, B, and C, then it has something random that's left over from a DVD or email or who knows what. But there's some random thing stored in here. It's not the number you think it is. Okay?
So is it work or not?
It'll work. Yeah, this statement should work. This won't give you an error.
So they make some comparison between the C, the alphabet to the lower bracket.
Say that again.
I mean the C, the alphabet should be 3 and the C, the lower part is 9.
Yes.
Different.
If you put C output here, and you want to see what the value of C is, what will come out here is 3. If you put C output here for C, what will come out is 9. In C++, this is a perfectly fine statement in C++. That's not an error. Right? Is it useful? It could be. If your intention is to make C twice as big as it used to be, this is a useful statement. But maybe that's not your intention, so it's not useful. But C++ will not object to this. It says that's okay with me if that's what you want to do. How does it actually work? There are other places inside the computer. We have these ones labeled, but the computer has its own spots that are set aside by C++ to store the intermediate results and to do things like operations. So when you put this command in, C equals C plus C, it comes into the C location, pulls out that value, and then it goes into the jump location inside, the intermediate location. It puts that value in, it pulls it out again, it puts it in again, it adds those two together, it takes the result, and it stores it back in that location. So if you put this command in, say down here, and then put another C output, what will it write? 18. If you put it in again, another C output, what will it write this time? 36. Maybe now you put in this one. And then follow it with an output. What will that output write? 0. That writes 0. Now let's do another one of these. Put in another output. What does it write? 0. Okay? It's dangerous. It's very powerful because it'll do all these calculations. But it's dangerous because the logic is not exactly like algebra, right? This statement doesn't mean anything in algebra. C can only be 0. In this statement, C could only be 0. In this statement, C could only be 0. All of these statements in algebra, C has to be 0. That's the only way C can equal to C plus C. It's the only way that C can equal to C minus C. That's in algebra. But in the arithmetic that C++ is doing, all of these statements have a different number answer. Even though it's the same thing over and over again. We write C equals C plus C, we get a certain number. You write it again immediately, you get a different number. You write it again immediately, you get a different number. So it's dangerous. You have to be sure that it's doing what you think it's doing. So that's why, back at the beginning, one of my suggestions is, when you first write your program, put these C output commands in everywhere to program. Write out all these intermediate results and check it with your calculator and make sure that every step is doing what you think it's supposed to be doing. Now, I can tell you I've spent many hours of my life going through line by line in some program, scratching my head. Damn, what is wrong with this thing? It should be giving me some number, it's giving me something else. Trying to figure out where I had some bad logic. Right? The computer says, it's fine with me, I'll calculate that, no problem. Here's your answer. That's not the right answer. What's wrong? What are we doing wrong? How come this computer doesn't work? There must be something wrong with the computer. That stupid computer, it's a piece of junk. Doesn't know what it's doing. The problem is always in the computer, it's not up here. I wish. Okay, so Casper, back to your question then. Are you... Okay, so I gave you two possible suggestions of how you can fix it. One is kind of the long way, but it's clever, and it's also a nice practice for the long term. And that would be that you write your own routine to do cube root. And you can give it whatever name you want. A new C++ program called Casper's Cube Root. Right? And then it does what Tim suggested, right? With the log, you could do that. But another thing that should work is I'm almost certain that C++ will let you put in a fractional exponent. So a cube root is the same as raising something to the power 1/3. I'm not sure that it will let you do a negative exponent. Does anybody know? If I needed to calculate this, that's equal to x to the minus 2. But I'm not sure that you can put a negative exponent into C++. I'm not sure it will allow that. But if I wanted to calculate this, that's equal to x to the 1/2. It will let you put in 1/2 for the exponent. So what would be really nice is if I could do this. And it lets me put in both a negative exponent and a fraction. Right? I mean, that would be really convenient. Then if it'll do this, it'll do anything. Okay. So that was from exercise 2.2. I think your question, I think, was related to 2.2. That was still on the average routine. So you did a good job of finding errors. The end of that exercise was sort of a strange thing. It said put some errors into your programming so that it doesn't work right. You see what the computer says. So it sounds like you did a good job of putting errors in the program. Does anyone else have a question about 2.2, exercise 2.2? How about exercise 2.3? Casper asked one. I think we've answered it. Are you satisfied? Okay. Anybody else have a question about 2.3? Yeah.
So once you see I have two and I just want to other command have to express and person.
Why do some commands have 2 indel? Yeah, I don't know. Are you sure some have 2 indel?
Yeah, I erase one and it's still wrong.
Yeah, I don't think you ever need more than one. Why do you think you need more than one?
Because the example is right in the program. So some reason I don't understand.
Yeah, I don't have an explanation for that. I'm not sure it's true. Right? If you had a command that has only one indel and it gives you an error message that says you need There's two N-bells on the end of the CN command. Let's look at it together. Okay. Alex, which lecture was it? 2.3? Can we look at lecture 2.3? I guess I'll erase this. Yeah, I think it's important maybe just to, I'll re-emphasize one more time the general idea that came out of your question, which is that commands that make absolutely no sense in algebra make perfect sense to the computer in C++, and also in math, also in Fortran. So, I can write something like this, and the computer, as a command inside of the language, has no problem with this idea. No problem with it. That's scary. I mean, maybe take the A out and put 10. So if I start off and I have the value of y, let's say it's stored as 0, and I run this command, then what's the new value of y? 1, right? The computer has no problem with that. So there's a part of the memory that is the intermediate area for doing the calculation. The computer goes to the part of the memory where y is stored, it brings that number, it does the calculation 10 to the y, and it takes that answer and it writes it back into the memory where y is stored. So when it pulls the value out, it pulls out a 0, but after it makes the calculation, it writes 1 back into that same memory location. The computer's got no problem with that. So again, I just caution you, that's a little bit, makes me always a little bit nervous when I'm writing a program. That it can do a calculation like that with no problem. All right, now here's one you didn't ask me about, maybe you should have. Let's say that we did this. I'll put a multiply sign up there. And actually give it some good. What happens? What's the answer to this? I'm going to propose two possibilities. Right? The first possibility is, and let's say we start off with y equal to 0. So the first possibility is it pulls y equal to 0 out. It goes into the intermediate calculation. It calculates exponent 0. Now it has the value 1. It puts that back in. Then it goes out here and it does 3 times 1. That would be 3 more, plus 1, so the output would be 4. The other possibility is it takes 0, it puts it in here, it gets 1. It puts 0 in here, it gets 0. And so the answer is 1. Okay? What happens? What really happens? The second one. Right? It doesn't restore the value of y until the whole calculation is finished. Then it changes the value. So this is what you really get, not this one. That's lucky, right? Think of how terrible it would be to try to figure out what the right way to write the statement is. If it took the first result, stored that, and then calculated the second result to give you this, that would be impossible to figure out. In a lot of different problems, maybe not this one. Okay. Are we up? Good. Maybe do the, let's get rid of this and then we hit the display button, the one next this guy. Thanks. Okay. By the way, do you know how to pause it? I still have about 50% success rate of trying to. Can you go back and pause for a minute? Pause after the one that shows the statement ending. you need to put the semicolon on the end of the statement to stop the statement. So I'm going to jump ahead to MATLAB for a minute. MATLAB will let you put this statement in like this. What's interesting about MATLAB is if you don't put the semicolon on, it automatically generates its own write statement and writes out what the value of A is. So I just told you a minute ago, I think it's really good practice for you to put in a C output statement over and over again in your program, maybe after every single calculation, so you can check the intermediate results. In MATLAB, the default is that it writes every statement, so you don't have to do that. It's really nice. That's one reason why I like MATLAB better than C++. It's more advanced. In MATLAB, when you put this on, that stops the output statement. So you only put that on if you don't want to see the intermediate result. But in C++, you have to put that on. So that's one point I wanted to make. The other point I want to make is, because this ends that statement, you can begin another statement. We talked about this before. You can put B equals A, it could be the very next statement, that's fine. You can also add your comment onto the end of the same line, so your program doesn't have to get really long. So the next thing you do could be to put a comment, and then say, here is where I define A. Something like that. Okay. And that comment can go at the end of that line. It doesn't have to have its own line. Okay. Nice haircut. Maybe I should talk to you about where you got it. Okay. Which slide, do you remember which slide was the question you asked me about? Almost at the end? Okay. We'll start at the end, maybe and back up. Yeah, go up one. Let me ask you, are you familiar with C++? Do you use it a lot? Or? Yeah. So MATLAB has a built-in help command. You can always look up the syntax and then you command in MATLAB. As far as I can tell, it doesn't exist in C++. That's very elegant. Yeah, so your question, I just want to make a general comment. Your question is about syntax. What does this word mean again? This is the form of the command. So we have to get the syntax right. And specifically, you're asking me, how many of these do you need at the end? So I hate to keep, I don't want to say too much negative about C++, but in MATLAB, built into the program itself, you could do this, you could say help CN. And this command will, on the screen, give you the guide for how to create the correct CN statement. It'll tell you the correct format. So you can find the answer to the question about how many LNs you need. Right in the middle of MATLAB, you can just type this command and get the answer. But I haven't yet figured out if it's possible to do that in C++. I haven't figured out how to do it. So I don't know where a good source of figuring out all the syntax of the C++ commands is. That's a note. I should make notes to myself. That's something I can look up. Let's all try to find that tonight. I looked under help. There is a help tab at the top of C++. But even that tab, as far as I can tell, wouldn't give me the syntax. Do you know, by any chance? Do you know if it's possible to get? Yeah. Do you know if it's possible to get the syntax of C++? Okay. Because it's very easy in MATLAB. Just type help. In fact, in MATLAB, just to jump ahead, when you first start in MATLAB, you can type this command, help, and it'll show you how to use help. Then you can use help to find the answer to the question you're looking for. So first you do this one. Now you learn how to use help. And then you do this one. And you learn how to use that command. So MATLAB is really nice for that. I should make a disclaimer statement about MATLAB, okay? This will sound a little bit like a conflict of interest maybe, but my aunt, her cousin, is married to the guy that invented MATLAB. So he's sort of related to me, but I have no financial interest in MATLAB. So when I say nice things about it, it's strictly as a user, it's not because I'm trying to sell it. Okay, what should we do now? We didn't really answer your question yet. Why don't we start at C++? Start the executable version of it, the regular. And you didn't happen to write down the name of the example that it appeared in, did you? Yeah, there were a lot. I think this lecture had a lot of them down here. Was it one of these? Do you remember? Bit location. Okay, so let's open this one. Yeah, unfortunately, I think you have to go into the directory to find it. Well, I think they're all in there. If you go back to the disk that I handed around, the thumb drive, it had a section called, yeah, go up. Maybe it was on examples. Maybe you were on the right one. Sorry. This one. Okay. These down here. Yeah, so let's do a compile and run. The system cannot find the file specified. Which file? Yeah, which file? It's missing some file. Which one? Okay, that's not a very helpful message. It says I can't find this file, but it doesn't tell you what file it is. Okay, so let's pause for a second. So, where's their file that I can't find? Did you try it again? Can't find C out. Oh, this is one. Yeah. So you need indel on this. I don't know if this message doesn't appear to go with this error, but it looks like there's an error on this line. There should be an indel at the end of this line. So let's edit that and try putting it in there. Might as well copy those too. You need to put the, yeah. Okay. Let's try it again. Let's try to, it runs on that computer, but not on this computer? Oh, that's not good. You downloaded the program from the same website. Alex, just try compiling this again and see if it gives the same error. This one. Yeah, can you hit the compile? Yeah, so it gives the same error. Well, I think the file is not binary, it's up there, right? Do you have it? Alex, the directory that this program is in, do you have a file called Uptown? Or actually, it should open a computer screen, right? It should open a DOS screen for this. You think this is running? Did you fix it, or is it the same? It should be the exact same program. So how can it run on yours and not on his? Yeah, you know, there's something wrong maybe with the way that your C++ got downloaded from the website. Maybe you should reload your C++ compiler when you get home. Okay, so now you can put the, you can go ahead and type it in this one. Okay, so finally, I think, back to your question. So what exactly was the question? I think we finally have a working version. Yeah, why are there two down here? Yeah, I don't. As far as these two, I don't think you ever need two. So I'm going to propose that we try removing one and see if it works. It could be that. Say it again. Yeah, maybe that's what it does. But let's see. Did we see the output yet? Where does it even number the line? Yeah, I think you have to go to, I think it's an execute submenu. So it didn't, taking it out seems to cause the problem. Sorry, get out of the way. It's a good question. I'm not able to, I don't know the answer off the top of my head. I'll have to look that up. But it doesn't look like it worked without one. So it does apparently need them both. I think the first one, maybe the first one goes with, yeah, I don't know. I don't have a good explanation. Yeah, I don't know. Yeah. Okay, just a second, I can't hear it. Yeah, I'll have to maybe you can ask me again at the end of the class. Is that okay? Okay, all ready? All right, other questions about exercise 2.3? Does anybody have another question about that? Yeah. Yeah, I guess I would ask you to repeat it. Everybody, can I have your attention for a second? We're trying to discuss the problem. I really can't even hear her. And I know you can't hear her. So the question she's asking could be important. Maybe you would like to hear it, or maybe you'd like to hear the answer. Okay? Okay, please repeat your question. This is on exercise 2.3. Okay, would it help if I point at it while we talk about it? Which command? Double in, we're talking about, yeah, this one down here. Yeah. I'm sorry, I still don't understand exactly what you're saying. You don't get the double in, you said? Yeah, so this. Oh, you don't get this. Yeah, why not? Okay, sorry, it took me a long time to understand your question. Why doesn't this appear when you write it? Why does it say you entered up down of? But no double in. Did you run the? Let's go ahead and run the program and look at the output. This is inside of the quotation marks. The things inside of the quotation marks, we think they're supposed to appear, but it doesn't appear here. Right? Why not? Okay, the backslash is a control character that helps format the line. So if you put a backslash in, the thing that comes next is treated like a command. And in this case, N is to give it a new line. So backslash N makes it go down 2 lines. That's why there's a space here. Okay? It's an excellent question. So it just makes the screen a little bit easier to read. If every line came immediately after the next one, it wouldn't be so easy to read it. Yeah, put it outside of the quote marks. Yeah, I'm pretty sure, again, I apologize that I'm not as knowledgeable about C++, but I think you can put that inside or outside. I think if you put the backslash in, it automatically treats it as a command no matter where it is. But that might be something to try. Try putting it outside. See what happens. Who's controlling this one? Is that you, Tim? Yeah. Can you put these? Can you put the backslash outside of the quotation mark? Yeah, just put it right just before it here. Well, actually, run it right now without putting it anywhere. Let's run it again. Yeah, just go ahead and compile and run it. Well, don't put it back in. No, don't put it in. Now run it. Okay, so let's see the difference. Okay, now let's try putting it outside of the quotation mark and see what happens. Okay, so it doesn't like that. So try it again by putting, let's put those, put the double things in between that and the, we're running together here. Yeah, now let's try that again. Now it still doesn't like it. Okay, so syntax for C++, this has to go, I've got it backwards right here. That gives you a new line. It has to go inside with the quotation marks for the character. So you can put that right in here, and that will cause a new line. You can use. I don't think there's an example in here. Yeah, at least not in this example. But it's common that when you're writing an output, you might want to have a single write statement that actually writes several lines. So you don't have to use different C output commands for different lines. You can put it all into one command and put this in the middle of it. So it writes the first line, goes down, writes another one, all inside of a single C output command. That's okay. That's why they have this. Okay? And if you want to make spaces, of course, you could always put it at the end of the C output command above it, that one, so it will automatically make a space before it begins the next one. Or like this, he put it at the beginning of the next line, so it made space at the beginning of the next line. All right, so you can put that anywhere inside of it, including in the middle. Okay. I'll bet there's a new page command too, although I don't know, did anybody try it? There's probably something like this that would skip a page, but I don't think it would be useful on the C output, because skipping a page inside of the DOS window wouldn't really matter. But if you're writing your output to a different device, something besides the DOS window, skipping a page might be useful. So I don't know, but I'm guessing something like this exists, but we'll try it. But in the meantime, back to exercise 2.3. So thanks, it's a good question. And this is helpful that we now know this. Any other questions from exercise 2.3? Did anybody try 2.4 yet? Yes? Still looking? Okay. Are there any questions from the lecture slides that I had you read? You did 2.2 and 2.3 last night for the lecture slides. Okay with that? So we're all caught up, we're up to speed? Okay, are you ready to go to 2.4, 2.5? Ready? Okay, so for tomorrow then, look at, you should remember the order. Read 2.4, 2.5 in the lecture book. Look at the lecture, 2.4, 2.5, the exercises. And I think tomorrow what we'll do, we'll back up a little bit and we'll start making homework assignments. We're already past the point of some of the first homework assignments, but I haven't officially assigned them. So let's have one more day of practice, and then tomorrow we'll start doing homework. Okay, any questions? 2.4, I think this is when you start to get into the if, then, while, that kind of logic. So basically all of these are used for what's called generally branching. So that's the next logical topic you're going to read about and hear the lecture on. And the idea with branching is that lots of times when you're running a program, you have to make different decisions based on what's going on. Okay, so I'll give you one common example from dynamics. You probably just had this in 208. If you have a block sitting on the ground, at this point there's something called the coefficient of friction. Did you talk about dynamics? Yeah. And did you talk about static coefficient of friction and dynamic coefficient of friction? Okay, so let's say you're writing a program and you're trying to analyze, maybe you've got a hill and the block is sitting on a hill. Oops. And you want to analyze, first of all, how hard do you have to push the block to get it to start moving? And then afterwards, what's the motion? How fast will it go? So you can analyze to get the initial push based on one coefficient of friction. But once it starts moving, you need the other coefficient of friction, the dynamic coefficient of friction. So inside of your program, then you want to branch, right? Where you make some calculations, and then you get to the point where you want to know whether or not it's moving. And if it is, then you go one way using one mu. And if it isn't, then not zero, sorry, static. And if it isn't, or if it isn't, use static, and if it is, use the dynamic. So that's a simple example, but that's an example of when you want to use branching. Some very, very important engineering programs have thousands of branching decisions inside of them. You have to constantly change your mind about which way to go. I'll give you one simple example from my own experiences. There's a lot of very high-end jet airplanes, and they can fly at what's called a very high angle of attack. What's angle of attack in an airplane? Who knows? It's not a military term. It's just a generic flight term. It sounds like it with attack. But what is the angle of attack?
It's a horizontal and
Yeah, it's the difference between the angle that the plane is pointing and the angle that it's moving. Right? So a lot of airplanes, you usually think of an airplane as flying like this, or maybe it flies like this. So it looks like it's moving along the axis of the plane. It looks like the motion is right down here. But actually that's not what happens most of the time. Most of the time the airplane is actually tilted a little bit compared to the way it's moving. So it might be flying like this. Okay? Or maybe it's flying like this. Not very long. Start doing that. But that angle, the difference between the way it's moving and the way it's oriented, that's called angle of attack. Most airplanes, if they exceed a little bit of angle of attack, they become uncontrollable. So it's something to be nervous about if you're in charge of the airplane. Some very, very high-end airplanes are able to fly at an incredibly high angle of attack. But when they do this, when they fly at a low angle of attack, the air that goes over the plane goes around the plane nice and smooth. That's how it's designed, to reduce the drag and make it very efficient. But if the airplane starts to rotate up at a high angle of attack, it spoils this air. So now instead of going that way, instead of redrawing the airplane, I'm just going to redraw the direction. So let's say this is the way it's moving. So it's at a high angle of attack. Now instead of the air going nice and smooth around the plane, it crashes into this part of the plane, and then it turns into a bunch of junk air behind the plane. That's what makes it so dangerous. Is that air becomes really turbulent. It's just swirling all around. It's not predictable. So the airplane just starts going crazy. But some airplanes can handle it. The control system is so fast, it adjusts the wings constantly at a high enough speed that it can respond to that high angle attack. But it's junk air. So normally the flight control system would be based on a predictable model of how the airplane flies through regular air when it's nice and smooth. But when it gets into this, the model becomes unpredictable. It depends on the instantaneous conditions, and they change all the time. So inside the computer of the airplane, instead of having one model that decides how it's going to control the plane, there's hundreds of different models to control the plane, depending on what the actual condition is right this second. So inside of the control system, the computer that's controlling the airplane, there is a loop. And every time it goes around the loop, it makes a few measurements, and based on those measurements, it goes into hundreds of different models. Well, it only goes to one, but it selects one out of hundreds of different ways of making the next calculation, depending on what exactly this air is doing. Okay, so that's just an example of when branching is very, very, very important. We talked a little bit about finite elements one day. You know, a lot of real-world engineering problems have functions that do something like this. It's very nonlinear. And it can be hard to write a single mathematical function that actually describes this whole curve. So it's common to break this up into little pieces and treat each piece as a much simpler function, maybe a straight line. So there's a straight line in here, a straight line in here, but it's not quite the same. Another straight line in here, it's not the same. Another straight line here is not the same. Even the slope changed sign from being positive to being negative. So this function is made up of, instead of one really complicated math function, it could be made up of, let's say, 300 or whatever the number is. Very simple math functions. Straight line, right? It's a very simple math function, straight line. But it takes a few hundred to make an accurate representation. Now, if I'm writing a program that's supposed to calculate something based on the value of the function, rather than putting x here and having one single calculation to figure out what it is, I have all of these little functions set up as separate pieces. And there's a logic that when the program begins, it gets the value of x, then it goes to the correct straight line to figure out what math accurately predicts what's going on in that little region. Okay? But an instant later, maybe the value of x has changed over here, so then I have to jump through the loop again, make a new decision, and go to a new place. So that's another example of why you might need branching inside of the program. Let me give you a more fun example. I talked about programming craps. right? I propose maybe you want to program computer programs. So you have a random number generator that's generating a card. And if you're going to do an accurate representation, the first time it goes through the loop, it should have 52 possible outcomes for the card. But the next time it goes through the loop, it should only have 51 possible outcomes. The one that you've already dealt should no longer be possible, right? I already got the ace of spades, so it's not available anymore. There's only 51 available. And the next time it goes through 50, and the next time it goes through 49. But you don't know in advance which one is going to go out first, which one goes out second, and so on. You don't know that. So inside of the program, you need logic that every time you pass through to get the next card, that logic removes the possibility of dealing one of the cards that you've already dealt out. Okay? So there's a lot of branching, there's a lot of logic that you have to program that can successfully do that. Who plays online poker? Anybody? Yeah, do you make lots of money? It doesn't really look like you make lots of money.
Thanks.
Yeah. No offense. Okay. But yeah, online poker you can do, but lots of other things, of course, too. The phone system. You know, when you call a mobile phone number, think of all the branching that goes on. First it takes a country code, decides what country it's going to, then there's a regional code to get to a certain part of the country, and then every digit in there narrows the number of people. And in the end, your phone number might only differ from somebody else's phone number in that very last digit. So when the call begins in that branching program, it's got millions and millions of possibilities, but each digit moves it into a smaller and smaller possibility. And finally, that last digit, there's only 10 people out there. Right? It depends on that last digit. You get it, hopefully, to get the right call. Okay? The old phone system branching was usually a woman sitting in front of a great big board that had a hole for everybody's phone. And when the call came in, it came in on the cable, and she would take the cable and ask, who do you want to talk to? I'd like to talk to Joe. Okay. And now you're talking to Joe. That was the branching. So, I hate to say how old I am, but I remember that. It's not like that anymore. It's all completely automated with these kinds of statements. So, as you go through this, what you'll see is combinations like if and then. So usually what happens is you'll have a command that looks something like this. If, let's say, x is greater than 2. Okay? And then, and this begins a whole sequence of commands, a whole sub-program. So up here somewhere you calculate x, or maybe you input x, and then you get to this statement, and it takes the value of x and it would compare it. In this case, it would compare it with 2. If it's bigger than 2, it does these commands. Somewhere underneath here, there's another command that says, usually it begins with the word else, and there's another whole set of commands, another subprogram. So if x is not bigger than 2, it does this set of calculations. If x is bigger than 2, it does this set of calculations. It does not do both sets. It can only do one set or the other set, but not both. Right, so that's the idea of the if statement, an if and then. While works fairly similarly. Often in the while statement, what will happen is you'll have something like while x is greater than 2, but now as part of the subprogram, the value of x gets changed. So it keeps running through this loop, and it keeps changing x, and as soon as x is no longer, as soon as this is no longer true, then it goes on to the next line. And down here somewhere is a statement like in while. And that tells it this is the end of the loop that's while. So it'll keep repeating this for as long as x is bigger than 2. If it gets here the first time and x is already not bigger than 2, maybe x is equal to 1, then it never does this. It just skips it. These two pieces of logic are actually more or less the same. There's not really any difference in the way that the logic works. The syntax of the commands is a little different, And it actually is common in these that you also might change the value of x. Now, there's a third thing called a do loop. And usually it starts with a command like do, and it'll say from I equals to some number like I, which is an integer. And it's often called a counter. A counter because it counts. So let's say from I, typically you go from 1, but not always, it can be something else. Let's say 1 to 100. And then you can go by whatever jump in the integer value you want. But this version of it would go from 1 to 100 by ones. So this will pass through, and then it'll end the do. Down here, some subprogram. So it comes up to this statement the first time. It makes I equal to 1. It calculates this subprogram, which may or may not have anything to do with I. Maybe I never appears in here. It's just a counter. But you can use it. You can use I inside of here as a variable if you need it. Then it gets to the end and it goes back up here and it makes I equals to 2. And then it repeats all these commands until it gets to the end and it makes I equal to 3. And so on. So this do loop would execute 100 different times. Each time I has a different value. You could do this. The first time through I is equal to 1. The second time through it's equal to 11. The next time it's 21, and so on. You could do this if you wanted, if you're really kind of crazy. So the first time through I is equal to 1, the next time it's equal to 28, the next time it's 55. Okay? So this also, logically, you could make this do kind of the same thing as either of those two. Right? One difference with the do loop is, by looking at these three numbers, you can tell exactly how many times it's going to go through this set of subroutines. Right? If I put, let me go back to 1. It's going to do this 100 times. Over here, it's less predictable. It's only going to do it for as long as x is greater than 2. That could be 1 time, it could be no times. It could be a million times. It just depends on what the value of x is. And same thing over here. So the number of passes through the loop in these cases is not known in advance usually. But it could be, because it could be that the only thing that you change in x inside of here is that every time it goes through, you subtract 1. So maybe somewhere down in here you have a statement, one of those dangerous statements we talked about today at the beginning of class. You have a statement that looks like this. So every time through, x is exactly 1 number smaller. You can start up here with, say, x equal to 101. And it'll keep going as long as x is bigger than 2. And so you know it's going to go through this loop exactly 100 times. So that would be just like this one. But more often, if you use this kind of logic, it's not because you're making such a predictable calculation for x. Usually whatever is happening for x is a little bit unpredictable, like that airplane flying along in the wind. And so you're not really sure what's going to happen in the next instant. Somewhere there's a sensor on the airplane that's measuring something, and that value is affecting x. So it's while you're measuring that you update x, and you don't know in advance when it's going to change. So this is unpredictable how often this will run. This is very predictable. Okay? Then you can do something called nested do loops. This is called a do loop. In a nested do loop, there would be another one. Let's say j from 1 to 10 by 1s. And down here there's another in do. So it comes in here and it sets j equal to 1. And then it does this loop 100 times. I equals 1, I equals 2, I equals 3. And after 100 times it's done with this loop, then it hits this command, and that tells it to go back up here, and now j is equal to 2. And now it does the inside loop 100 more times, with j equal to 2. So the combination of these two do loops would be to do the commands that are inside of here 1,000 times. Right? It does this 100 commands 10 different times. And these two don't have to be right beside each other. You could have a sub-program in here, so that by the time you start this loop again, something has changed. You calculated some new thing. The first time through, j is equal to 1. Next time, j is equal to 2. So you calculate new starting points, and then you do this 100 statement do loop. And you can also have more sub-program in here. And you can nest the if, then, while kinds of loops. Also, you could have those nested in here. So maybe you take one of these kind of loops, and it shows up as part of this subset. So 10 times on j, you start this loop 100 times on I, that's 1,000 times. And each time that you do that, you get stuck inside of this loop for as long as x is bigger than 2. So maybe out of those 1,000 times, some of them x is now bigger than 2, it never does this loop. Maybe other times x stays bigger than 2 for lots and lots of cycles, and it does this loop a lot before it goes on to the next value of I and then the next value of j. Okay? See how this works? Now, let's go back to that example I gave you about the automatic landing system. Right, so we calculate 5 different variables at 1,000 points. Was it 5? I think we said 5. We want to calculate altitude, we want to calculate range, we want to calculate speed, we want to calculate pitch, we want to calculate roll. 5 different things, and we want to calculate it at 1,000 points in time while the plane is coming down to the runway. So I might set up this do loop where I have on the outside 1,000, right? And the thing that changes in each pass-through is the time variable. And on the inside of the do loop, I calculate those 5 things. So that would be an example where maybe I use a loop of 1,000. And the only thing that changes on each pass is that time variable. Then I calculate a new altitude, a new speed, so on. But remember what else I said about that landing system. I don't want it to work just when it's sunny and 30°C. I also want it to work when it's rainy and windy. Or maybe it's rainy but not windy. Or maybe it's windy but not rainy. Or maybe it's 10°C, or maybe it's 50°C. So I want it to work over and over again for all those different conditions that the airplane might experience when it needs to land. So I might nest loop after loop after loop. Maybe the outside loop is the temperature loop. So I started, 0°C, and I go to 40°C. And I calculate it for every 0.5°C. So that loop has 80. That's 80 loops. That changes the temperature each time. Inside of that, I try the wind. Maybe the next loop is for wind. I go from 0 kph to, 100 kph. If it's more than 100 kph, we're not going to fly today. But up to 100 kph, we still want to be able to fly the airplane. And maybe I decide 1 kph is good enough for the difference on that loop. So that loop has got 100. 1 for each kph. Then inside of that one, maybe I do relative humidity. Right? Some days the air is nice and dry, 0%, 5%, 10%. Although I have to say I can't imagine that around here. So from around here, maybe start at 70%. Between 70 and 100 is good enough. But I have a loop that represents the humidity, because the humidity represents how dense the air is. And the density of the air has a huge effect on how the airplane flies. So then I have a third loop, it's all nested. So on the outside, remember, there's a big loop, and that represents the temperature. Then inside of that is a loop that represents wind speed. And for every single temperature, I go through all of the wind speeds and make the calculation over again. But also inside of that loop is humidity. So for every temperature and every wind speed, I do a loop that looks at all the different possible humidity. But wait a minute, some days the plane is full of fat people, and some days the plane just has 5 skinny people. So I need another loop that represents the weight of the airplane. And I want to try that for every single combination. So now I've got a loop on the outside for temperature, then a loop for wind, then a loop for humidity, a loop for weight of the airplane. Right? Are we done yet? No, there's that gas thing. Right? Some days the pilot's a cheapskate. He didn't buy gas for the last 3 airports, and he's almost out of gas. But sometimes he's not a cheapskate, and he filled the plane with gas at the last airport and still got a lot of gas in it. So I do a loop based on how much weight is in the wings. Okay? You know, and then there's different airlines, and they all fly a different airplane. Why can't they all just get one airplane? No. Some people have a Boeing, some people have an Airbus, they have a big Airbus, they have a little Airbus, they have a big Boeing, a little Boeing. So I need another loop for all the different airplanes. And so by the time I'm done simulating all of the possible landings of all these possible airplanes under all the possible conditions, maybe it's millions of cycles total. The outside loop is 100, but then the loop under that is another 100. So these two together are 10,000. But then there's a loop under that on humidity. I think we have 60 or so loops for humidity. And inside of that is another loop for fat people or skinny people. Maybe there's 50 different versions of that. And gas. And the total number of times the program's going to go through those calculations is the product of all of these things multiplied together. You can easily get to 1 million. You can get to 1 billion. What's the biggest number you get to? There actually is a biggest number. Right? There's a biggest number because, remember, every variable that gets stored, even if it's double, it gets to store 12 digits, and then there's the exponent, and then it stores a limited number of digits, which I think is 2, but I'm not positive, for the exponent. So the biggest number is 9999999, 10 to the 99. So I can't do anything more than that. I have to cut it off and start over again a new program with a different initial condition. I need to run one of them. Okay? So when you look at these nested do loops, you can understand things like, when I told you the other day, when I was in graduate school, the computer program that I was using to write my thesis took so long. It would run for 6 hours or 8 hours. This is why. I would come into my office at 9 or 10 o'clock at night to start it up again. I'd go home and sleep, come back in the morning, it would finally be done, and start it up again. Go home and have lunch, come back, start it up again. It was a miserable existence. But I finally. Okay, any questions about this? We talked about the round-off error, right? You did a nice experiment by comparing float with double. You didn't see a difference in your calculation. If you were doing millions of them, you might see a difference. But it becomes a lot more important maybe to use the double. Yeah, absolutely, it's possible. Does anybody pay attention to supercomputing? So-called supercomputers, the fastest, biggest computers in the world. They're measured now in a number of what are called floating point operations. Floating point operation per second. So you know what a float is. You know how these numbers are stored. Remember, the function of the exponent is to move the decimal point up and down wherever it should go. So that's where this notion comes of a floating point. It means the decimal point can be put in there arbitrarily because you can control the exponent at the same time. All right, so a floating point operation could be to take two numbers and add them together. That could be one floating point operation. So nowadays, there's a big race to see who can build the world's fastest supercomputer. It's actually been going on for 20 years or 30 years. The leader keeps changing. You know, somebody builds a super fast one, and then somebody else builds one a little faster. So does anybody have any idea what is the maximum? And then, by the way, this flops, the F-L-O, I guess you skip that one, O-P-S. So they call them flops. Floating point operation per second. What would you guess would be the maximum floating point operations per second in a fast computer nowadays. One of the things that limits it, and the thing that used to be by far the hardest thing, was reading and writing the numbers back and forth out of memory. That took longer than doing the operation. If I write A plus B, C equals A plus B, the floating point operation is to add those two numbers together. But to get to that point, I have to go into memory and grab A. I have to go into memory and grab B. So it's two operations of getting those numbers, then I can have them together. So it turns out that the reading and writing of that information back and forth to memory is usually the thing that takes the longest. But still, humans have gotten better and better at it. So how good are we? We're all humans. Right? What's the state of the art? What's the maximum flops? Maybe this will be fun homework tonight. Google it. Figure it out. World's fastest computer.
So if we put this floating point operation, this would be harder, right?
If you put double, yeah. Well, it's a good point that when you're comparing flops, it's important to make sure that you're comparing the same size numbers that are being processed. We've talked in C++. C++ has what I think is very old-fashioned float with 6 digits, double with 12. A lot of the more advanced compilers like Fortran, there are versions of Fortran that store 128 digits. So a flop in Fortran should probably take that. It's 128, not 6. That's a big difference in the amount of numbers that go into